Welcome back. In our last video, we learned that a single neuron is essentially linear regression in disguise. But to truly understand how neural networks process information, we need to establish some mathematical foundations. Today, we are covering functions, the mathematical concept that's at the heart of everything neural networks do. Don't worry, we will keep this practical and visual. By the end of the video, you will see exactly why functions are the perfect tool for understanding neural networks. Let's start with the basics. What is a function mathematically? Fx equals to y. A function is simply a machine that takes an input and produces an output. Think of it like a vending machine. You put in your money, that's the input. The machine does something, that's the processing. You get a snack, that's the output. Here are some simple examples. Fx equals to x plus 5. What does it do? It adds 5 to whatever is your input. You just have to replace the x with your input. For example, if the input is 3, then the output is 8. And if the input is 10, then the output is 15. And if the input is minus 2, then the output will be 3, since minus 2 plus 5 equals to 3. Now let's look at the next example, that is fx equals to 2. What does it do? It simply doubles your input. If your input is 3, then output will be 6. If your input is 10, output will be 20. If your input is minus 4, output will be minus 8. The key insight is that functions are deterministic. The same input always gives the same output. Now here's where it gets interesting for neural networks. Function composition. What if we want to apply one function, then apply another function to the result? Fx equals to 2x, gx equals to x plus 5. We can compose them. G of f of x. Let's trace this with the example x equals to 3. Since we know the function definition, f of x equals to 2x and g of x equals to x plus 5. So at first we will compute f of 3. Since we just have to double it, so we will replace x with 3 and we get 2 multiplies by 3, 6. Then we will go for g of x. When g of x equals to 3, we know that in function definition for g of x we have x plus 5. That is, whatever the value we get from f of x, we just have to replace it with the x in here. So f of x, we in our previous step we got the value as 6. So we have the input for g of x as 6. So 6 plus 5 we get 11. So here's the result, that is 11. This is exactly what happens in neural networks. Each layer is a function and we are composing them. Layer 1 takes input and transform them. Layer 2 takes layer 1's output and transform it again, and so on. The power comes from chaining simple functions together to create complex behavior. Now let's focus on the type of functions we saw in our neuron, linear functions. The simplest linear function, that is y equals to mx, where m is the slope, how steep the line is. X is our input, y is our output. If m is equals to 2, then we get y equals to 2x. Steep upward line. If m equals to 0.5, we get y as 0.5x. Gentle upward line. If m equals to minus of 1, then we get y equals to minus x, that is downward line. But we can make this more powerful. Y equals to mx plus b, where b is the y-intercept, where the line crosses the y-axis. Remember our house price example? Price equals to 150 multiplies by size, then we add it with 10,000 multiplies by bedroom plus minus of 2,000 multiplied by distance, then plus 50,000. This is a linear function with multiple inputs. It's the same pattern. Multiply inputs by coefficient and add them up. So why does this matter for neural networks? Each neuron is a function. It takes input and produces an output. Each layer is a function. It transforms all its input. The entire network is a function. Input goes in, prediction comes out. Neural network, we can think of it as f of 3, then the input can be f of 2, then again f of 1, then x finally. It can be a chain where f of 1 is the first layer function, f of 2 is the second layer function, f of 3 is the output layer function. By composing simple linear functions, and we will add non-linear functions later, we can recognize faces in photos, translate languages, predict house prices, play chess at superhuman level. It also starts with understanding that We are just composing mathematical functions. Let's recap what we have learned. Functions are input-output machines. We can compose functions by chaining them together. Linear functions follow the pattern y equals to mx plus b. Neural networks are just sophisticated function compositions. In our next video, we will discover a major limitation of simple linear functions. I will show you something called the perceptron problem, where threshold-based decisions create sudden dramatic jumps that don't make sense in the real world. This will perfectly set up why we need smoother, more sophisticated functions in neural networks. Thanks for watching this video, and I will see you in the next video where we will explore why simple step functions fail. Bye.